All right, so continuing with our example of copper reacting with silver, we've set up an electrochemical cell, copper metal, copper wire say, and we have a solution of copper 2 plus here that is 0.2 molar, and then we have a solution of silver ions that's 0.1 molar, and then we have our silver electrode over here. So we have everything set up for this electrochemical cell, and we're going to hook a voltmeter up to it, and we can actually calculate what the potential, electrical potential for this cell would be. Now remember, under standard conditions, the electrical potential for that cell was 0.457. So I'll just write that for reference over here for the cell. And we're actually not going to use this value, although we could. There's a couple of different ways of using the Nernst equation, but I'm just putting it up here for reference. So we calculated that by simply taking the standard reduction potential for silver, subtracting the standard reduction potential for copper, and this is what we get. Now, if we want to solve for this cell, we'll simply calculate what the potential is for this cell, what the potential is for this cell, and then we'll use our cathode minus anode to determine the potential for the entire reaction. So again, we have, this is our anode, this is our cathode, and we can tell that that's the correct order because, again, this is a positive electrical potential. And if we did calculate it and we got a negative electrical potential, then we would know that we put the cathode and the anode in the wrong spots and just simply switch them around and try again, and you'll be able to determine, oh, this one should be the anode and that one should be the cathode. It happens. I used to worry about it, and then after I realized, oh, if it's a negative, I just change it around and do it the other way. So, no big deal. Now, we're going to write two Nernst equations for this. So, let's start with the cathode because it's cathode minus anode, so we might as well start with that one first. The potential that we want to calculate equals the standard reduction potential for silver, which we would look up in a table and find that it's 0.0799 volts. And then we'll use the log base 10 form of this equation. You know what? I probably should write out the standard reduction potential equation for silver. And we are doing reduction here. This is cathode. Reduction is happening. Now, this will help because I'll know the number of electrons, and the number of electrons is in our Nernst equation. And if you forgot, here's the Nernst equation again, and we're using potential equals standard potential minus 0.0592 divided by number of electrons transferred times the logarithm of Q. Now, I wrote out the reduction potential here because it will help us write out what Q is. So this is over 1 electron transferred times the log of Q. Now, we just need to write the equilibrium constant expression for this reaction. Solids don't go in, and it's a product. So I'm just going to put a 1 up here because I do have to have a placeholder for that. So this will just be 1. And then divided by silver ion concentration. And in this case, our silver ion concentration is 0.1 molar, so I'm just going to write 0.1 molar right there. Now, we just evaluate this expression, and that should equal 0.7398 volts. Now, we'll do the same thing for our anode, or our copper portion. I'll go ahead and write the reaction right over here. Now, we use the reduction reaction here, even though at the anode we have oxidation. We just use reduction all the time. And it is helpful that when we look these up in a table, they'll generally have the reaction written out in the reduction form, just like we're going to need it to be used. So here we go. We have copper plus 2 electrons going to copper solid. Now, again, the actual reaction that's happening is the copper solid going to 2 electrons plus copper 2 plus, but we always use reduction reactions when we're doing standard potentials. Standard reduction potential. Use the reduction reaction. So we write a Nernst equation for this side. Our standard reduction potential was 0.342 volts. We're going to subtract our 0.0592. We're going to divide by the number of electrons transferred in this reaction. In this case, it is 2. So we have 2 here. Log of, and again, it's 1 over, and then on the reactant side, we have copper 2 plus. And if we look up here, copper 2 plus was 0.2 molar, so 0.2. And if we evaluate this expression, we should get 0.321 volts. Now, to calculate the overall potential, again, it's just cathode minus anode, except in this case, we use our non-standard values, so the values that we got out of the Nernst equation. So we'll simply take 0.7398 and we'll subtract our anode, which is 0.321. So we'll just put a negative there, and then that should total up to 0.4188 volts. And that's the potential of our cell under the non-standard conditions. And you'll notice it is a little bit different from the potential at standard conditions, which was 0.457. Went down a little bit. And this is one of the reasons why, over time, the chemicals inside of a reaction would usually decrease in concentration. Well, at least the silver would decrease in concentration. The copper would increase as we go along. But we could see what would happen to the electrical potential over time by creating a graph using this Nernst equation to see. And you should notice that over time, the potential will slowly go down until it drastically drops off and the battery is said to have died when you use up all of one of the reagents and you're no longer able to continue. Now, that is an example of, here we know the concentrations, we're able to calculate what the potential of the cell would be. Let's do an example using the same system, except in this case, we're going to have an unknown amount of silver in the mixture. Now, to keep things very similar and speed the process up, I'm just going to write the line notation here. And we're going to keep the copper side of our cell the same. Same concentration, 0.2 molar, so we don't have to repeat that calculation. but in this case, we will have an unknown amount of silver. And let's say that the cell voltage in this case has been measured at 0.460 volts. All right. Now, what is the concentration of silver in this solution? Using this information, we should be able to find it out. Well, we'll also need the standard reduction potentials. Now, we have cathode minus anode, right, is equal to the cell potential. Now, since I kept this concentration the same, we know that the cell potential of our anode, which is where the oxidation is taking place, is 0.321, because we already did that calculation. I did that on purpose to speed things up a little bit. So we have a 0.2 molar concentration here. We have all of that. So the anode portion should be 0.321. So we'll just start filling things in here. Here's our anode. We don't know the potential of the cathode just yet. And we do know our cell potential because we had to measure it with a voltmeter. So if we use this, we can calculate the potential of our cathode to be, let's see here, 0.781. Because it's just 0.460 plus 0.321. Move that over to this side. So this is the potential for our cathode. Now we'll just use our Nernst equation to find the concentration of silver. So we use the standard potential of silver, which again we would look up in a table. It is 0.799 volts. And for reference, let's write the standard reduction reaction for silver again. And that's a solid. We'll write that on there because it's important for when we're writing our Nernst equation. Minus 0.0592 divided by 1 electron times log of, the Q for this is 1 over the concentration of silver. So 1 over concentration. Now it's simply a matter of solving for this concentration. So I'll walk you through how to do that very quickly. We're going to subtract over the 0.799 to isolate that. So I should get negative 0.018, and that equals negative 0.592 log of this. We'll divide both sides by negative 0.0592. So I'll just write that down here. Now to get rid of the logarithm, we'll raise both sides to the power of 10. And we should get 2.014 equals 1 over concentration of silver. And so we just take the inverse of this. We should get the concentration of silver equaling 0.497 molar. So those are two main uses for the Nernst equation, aside from being able to calculate an equilibrium constant. But This is a useful way of determining an unknown concentration, and measuring the voltage of a system is a very quick measurement. It requires very inexpensive equipment to perform, and so sometimes this is a useful way of finding the concentration of an unknown using the Nernst equation.